Okay. So, as you heard from Bert, that there's some debugging stuff. You saw Fedora doing some ridiculously crazy TLS stuff. And on a day-to-day basis, I don't have to do any TLS stuff, but I do have to do some debugging stuff. So you're going to hear more about debugging from me, and I'm going to leave all the TLS crypto questions to Fedora. So one of the things that we have as a problem is the fact that the concept of we need to be able to figure out how many people have ever had a memory leak problem in their node process. Oh, yes. Well, isn't JavaScript wonderful? Isn't everybody really happy they use JavaScript? Closures are a great thing. Promises also make memory leaks really fun to debug. So, you know, I know everybody wants them, but we also need to make sure we can do that. So I'm going to do a little bit of a quick demo here for some tooling that you may have already seen, you may not have, plus a little something new to tack on at the end. So the first thing, this is all about post-mortem analysis. So this is basically taking your running server in production and it crashes and you've got a core file. A core file is generated by your operating system. On Windows, they're called mini dumps. This is just a representation of all of the memory for your process at that point in time. It has all of the state you could ever hope to find out about your application. You probably just ignore it, or if you're on Linux, you didn't even know it was going to ever be written out because Linux doesn't turn that on for you. So basically, this mechanism is if you run Node and Node dies for a particular reason, it will leave this core file around for you. If you're on Linux, you type ulimit-c unlimited. You can do this on basically any Unic, and you'll get a core file. This is one primary piece that you have to have happen before you can do all of the subsequent stuff. And to appease the demo gods, I'm not going to use the Wi-Fi. So basically what I did is I went out into the cloud, and from a node process running out in the cloud, I grabbed a core file from a running node process while it was doing something in JavaScript. And there's this debugger that we have access to that's called MDB, modular debugger, so it's not as recursive as you might hope. So I will load up this core file here. And normally when you're working with a core file, how many people have ever had to debug a dynamic language before? Something with V8, yeah, Fedora, yeah. So basically what happens is you ask for a backtrace, and you're like, I'd like to see something useful about this, and you have really a whole bunch of hex frames in here that are just showing you where V8 decided it wanted to compile this function, and then it didn't have the ability to actually give you any symbol information for that. But you see you have down here, you have some C and C++. You can see all this happening down here with, we hit the main function, we do some libuv work, we come back into Node, and then we get lost in V8 land. So this starts off as being a great idea, and then you get lost in V8. So what ended up happening at Joyent is that they worked together to figure out how can we reconstruct all of this information. All of that information, your whole JavaScript program is in your memory, because that's just how we do it. We just like load it all into memory, and then V8 compiles it and runs it. And V8 keeps a whole bunch of this information around, otherwise it wouldn't be able to give you stack traces. So the first thing was, how can we reconstruct this? So they wrote this module called MDBV8. And I'm going to load that module. And so what you're able to do now is then type, now some of this syntax here, if you're used to debuggers like GDB and LLDB, this may appear a little esoteric, perhaps. But so : JS stack. And now, instead of just seeing hex frames in here, I can actually see the JavaScript frames that were happening. So we have some internal V8 things that are happening, function do callback. Guys, stop using closures without naming your functions, because otherwise it just shows up as anonymous. I mean, please, how many people will name all of their functions? You're liars. You're all liars. Sometimes V8 does really well at telling you where this was stored as, if you're on your prototype or something like that, and we can try and infer that. But otherwise, you know, this is the first step. You now have a stack trace. So if you ran into the process of, like, all of a sudden Node ran out of memory, which it probably will, because there's 32-bit process has a 1 gig limit, 64-gig process has a 1.5 gig limit, and you just held on to every buffer you ever saw, and then the process died. So when that happens, you have a core file, and you can at least find out when that allocation happened and when you died. Other things that would be actually useful here is, well, I actually would want to know some of the arguments that were being passed to all those functions. So if I do JS stack-v, I can see I'm in file HTTP.js, I'm in the offset into that file. Down here in this other anonymous function, I can see there were 2 arguments. One is a string, one's an undefined. So in our normal kind of emit pattern, this is something interesting. And then down here you can see here's my argument that was a JavaScript object. But if I'm debugging my application after it's crashed, I'm going to need to figure out, what version it was the source code that I was running. I'm going to have to check that version out, make sure I'm looking at the same thing in production that I had when this process died. Or I could just keep all of that information around because it's already all in the core file and just highlight that part of the function that actually was executing when this debugged. So I was using dtrace to grab this core file when something interesting was happening. So we know that that HTTP client request was firing, and this is the section that we're in. And then we can see this for other things. We have the end function that was emitting, and then down here we have an airback for the self request. So this closure was executing, and we have argument number 2, which is a JavaScript object. And in this pattern, we're expecting that to actually be a request object. So if I can take that memory address and type : JS print after that, I'm going to get something that resembles a JSON representation of that actual object. So you can see everything. This process is gone. It's nowhere near my virtual machine right now, and I have all of that information right then and there. I can now see and inspect this. I can ask it, what method was it and what was the path, and be like, oh, it was a post to that URL. And I can see all that information. So when your process died, you can actually have all of the state, and it's not like, well, I have the stack trace. I'm going to go add another, log line entry and pray to God that I see this, error again in production. You just get the core file, save the core file off to somewhere else, restart the process, and then you can come back and when you have time, actually inspect this process. So this is the first step that we did, which was add JS stack. So if you run your process and it just aborts for a libuv bug, a node bug, or running out of memory, you can get this by default. If you run your node process with node --abort on uncaught exception, every time you throw an uncaught exception, error, you can get a core file. So how many people have ever had an uncaught exception error? Now you're all eyes. Okay, there we go. All right. So every time you hit this, you don't have to worry about bringing in domains and trying to catch this or do process on caught exception. You can actually just get a core file for this, let the process die, and then restart it immediately, and then come back and know exactly where you are. So let's say it doesn't die in exactly the same place as you wanted it to be, or you actually wanted to find out what all of the memory was in this thing. We have this other concept, which is : find JS objects. Now, find JS objects is this real brute force mechanism. It scans all of the heap space for that process and says, are you a JavaScript object? Are you a JavaScript object? Are you a JavaScript object? And then tries to interpret that information. This is useful because if you're writing a binary add-on and all of a sudden the object gets collected out from underneath of you and you get a traditional kind of segfault because you were using memory that was freed out from underneath of you, you need to be able to go back and reconstruct all of that heap information. But it also shows you the live active use cases. So here you can see on the left, you have a representative object, the second column, the number of times we saw that object, the number of properties on that object, and then the constructor that made that object. So name your functions, name your object constructors, so that way you can actually know what things are. So here we have a whole bunch of objects that are actually in this. If I come back up here to the top, you can see there's a lot of objects in here. Okay, there were 5 million heap objects, there were 62,000 actual JavaScript objects, and we parsed all of those in 4 seconds. And I could be like, okay, actually I want to sort by the number of objects I see in here, and there are 2,200 error objects because V8 likes to keep some of those around, Node likes to keep some of those around, some of those aren't even real. That's the breaks, lots of arguments, objects that happen, slow buffers, those don't exactly exist in the same way in 0.12. We've got a bunch of objects that just aren't named. But so you can go through and be like, okay, well, I can figure that out. I can see, oh, well, I've got an array. I have 2 arrays that have 1,423 objects in them. And I can start to narrow down. If I have my function, if I have my objects with a named constructor, I can be like, oh, I'm leaking memory, and it's this object, and I'm holding a ton of them. Or maybe I want to find all objects that are client requests. So what we were looking at were client requests before. So I can find all those objects, and there are 14 client requests. So 14 in-flight, either previously collected or currently active HTTP client requests being sent out. And I can pipe all of that information back to JS prints. I can see all of those things, or I can ask them again for the method and the path. And now I can see all of these objects. And I can introspect over them. I can just do the normal shell pipeline kind of thing, like find this thing, find this thing, find this thing, print that thing, you know, type sed grep awk. How many people love Unix? I don't care, I love it. So, that's right. So you can do that, but maybe you also want to find out, you know, who's actually holding on to those objects, right? So like, memory leaks happen, you got to figure out who's actually responsible for holding on to that. You might be holding on to a single byte in a buffer, and that's actually holding on to the buffer slice underneath of all of that, and then wonderful things with reference-counted languages to be able to figure out what's actually going on. You can actually do -r to find JS objects. This is actually going to do all the brute force, and then it's going to be like, oh, I found an object and it's on this property, and that's what's holding it. Or it's in this array and it's at this offset. And then you can actually go through and find out all of the people in the entire graph of who's actually holding on to all of the memory in your process at that point in time. So you can go through that and make sure that you can figure out exactly what all this memory is that's being used by your processor. One last quick thing that I'll show on this particular part of it is how many people have ever, how many people consider themselves strong C people who've done a lot of C? Where's Fedora? What is it? Okay. How many people have ever prefixed their structs? How many people know what prefixing their structs actually is? Okay. All right. The idea here is that on your JavaScript object, you actually prefix your struct. So you have your objects, and then you might just say domain, and then is blah blah blah, right? But you didn't prefix that. So if I come through the core file to try and find that object that has that domain on it, I'm going to say I want to find the properties with everything that has domain. Well, great news. We've got 245 objects in this heap that actually have domain as a property on it. Whereas if I had actually named it, if I had actually prefixed it with something that was unique to my class, I would be able to come back and find it. So the idea here is to provide breadcrumbs for yourself. When you come back through things, you can actually find out where things went wrong. So we've heard about promises. I don't really have a lot of experiences with debugging promises, but how many people here use the async library? How many people have ever had like a waterfall or some other kind of pipeline go off the rails and not actually know where it died? Yeah, it happened more often than you like to admit it. Or it's happening and you don't even know it's happening. So basically part of the process of this is that there's an alternate module out there that you can use called vasync, which is meant to be kind of like a drop-in replacement for async, with the idea of observability and debuggability going on, and you can see exactly where in that async pipeline you were when it died, and be able to reconstruct that information and come back and know maybe you need to roll that transaction back or have all that information back. The key here is you're able to iterate more quickly on fixing your problems because you're fixing exactly what that issue is, even if you don't know beforehand by just the stack trace, and then you can come back and know exactly what you're doing it. And you don't have to add a log file, a log line entry and be like, maybe I'm going to see this again, and maybe it'll be 6 months from now before I ever see this, and I just lost, 10,000 more transactions because of it. So this is kind of the process. There are some caveats to what I've just shown you. This was all run on SmartOS. How many people have ever heard of SmartOS? Wow. This is fantastic. Okay, great. How many people ever used SmartOS? That's what I thought. Okay. So SmartOS is the operating system developed by Joyent, which we run in production on a day-to-day basis. We kind of like to think that it's the right place to run Node, and because we have all this debuggability and observability stuff with dtrace and MDB in there. And we're going to be doing a session. Max will be there and doing it in the castle this afternoon, showcasing MDB and dtrace, being able to show you how to debug your Node application in production. But I don't always develop on SmartOS, but I more often develop on OS X. How many people develop here in OS X? Yep. How many people wish they could actually do some of this memory leak analysis on their laptop? Okay, so now moving on to the next part of this, I'm going to show you here I am on my local laptop. I've got LLDB. LLDB is the debugger from the Clang infrastructure, which is built on top of LLVM. It's basically Apple throwing one of their fingers to the GNU folk because they don't like the licensing and they want to do it all their own way. So they built their whole tool chain, and this is what you get on OS X. So LLDB, I've got a core file here, node conf, and then I'm going to say, okay, so LLDB loaded up, and if I type backtrace, I have the same ridiculous JavaScript frames here that are meaningless to me, or I can say command script import v8 dot, where am I? I can load my little Python script, and all of a sudden it's like, oh, I found version 3.14 of V8. And then I can type JS stack, and now, ta-da, magic sauce, I can now do this stack tracing information on my laptop. And I can see, here we are with module compile, and here's an ASCII string that was sent to module compile, and if I actually JS print that, I can see that that's actually here. It's not as pretty as the other thing because this is just kind of a work in progress thing that I just started. But you can see that here's the actual source code for what happened, what Node does underneath the hood if you do Node-E to evaluate something. That's in there, and then I can actually even do, as of this morning, can do a little bit of objects. So here, this is the process object that you can see all of that information on. So basically, I can now do all of that without necessarily having to do MDB in SmartOS. So MDB in SmartOS works much better than this thing does right now, and it works for SmartOS cores and Linux cores. This will work on any platform that LLDB runs on. So basically, I also have this Linux box over here, you can name, and I can spin this bad boy up. And I can command import, or command script import LLDB8. Again, JS stack, surprise! So now anywhere LLDB runs, and LLVM works, etc., you are able to do this. How many people love Raspberry Pis, or Node bots, or something, Internet of Things? I can use a buzzword, right? Okay, so you're doing all these Internet of Things, and you're going to have all these wonderful problems on ARM and MIPS, and you're going to hit memory leaks. And you're not going to have any infrastructure inside of those environments because that infrastructure is precious. And you're going to want to be able to debug all of this. With LLDB, what you have is the opportunity, because of the design and architecture of LLVM, is to be able to do cross-target debugging. So from your Node bot, you're going to be able to take a core file and actually load it into LLDB and actually see where you're leaking all this memory from. So that's, I don't always get to, I have to talk a lot about Node. And I don't really get to talk about nerdy things about Node sometimes, and actually do things. So this is what I wanted to use this time for. If you're interested in playing with it, GitHub, Fontaine, LLDB. It doesn't have a README yet, but it's just Python. I'm sorry, there's not Node bindings to LLDB, though if somebody's interested, it wouldn't be that hard. And you can do it with FFI or whatever. So you can do all those kinds of things. So if you have interest in helping me work with this, I will be working on it further in Max's workshop. But Max will also help you with dtrace and understanding all of the other things you can do today with MDB. And that's all I have for now.